very good morning to all the guests who have come to listen my speech. Today is a day for green chemistry. Mainly we have speech on green chemistry. And at present I am working on focusing on the green chemistry because we know that chemistry is so important, but we have many problems, many effects because of our chemical experiments, the day-to-day experiments what we conduct. So I selected my track towards green, which is very attentive, or which makes us more important or focus on green chemistry because of pollution problems or environmental factors. So my speech will be on a small procedure which I have converted to the conventional method to the green method. Just I want to show you how we can design our experiments when we are all lecturers, professors. So how can we focus, how can we make the chemistry towards the path of green? Okay. So this will be the main content of my speech today, is about what is my aim and what is the scope of today's lecture or speech, and what about the introduction, green synthesis, and antibacterial studies, and also the final conclusion. Coming to the scope, my main aim is to show what is green chemistry, as I also know that everyone knows what is green chemistry, but I want to make just a recollection and what's going on about green chemistry. Then coming to the how we can design the traditional method of synthesis to the green method, how we can change the method, and then coming to how we can synthesize novel azomethines using the greener technique. Finally, have checked for the antibacterial activity, so that many strains which are very resistant to our body. So I have synthesized some compounds and found out that they are showing a better activity. So coming to the introduction part, so till today we have many drugs synthesized. I mean, daily we focus on synthesizing many new drugs. So the general method what we follow is molecular manipulation. We just substitute some groups or remove some groups, attach some groups, and make new molecules daily. And coming to the infections, bacterial infections, viral infections, fungal infections, these are very important. And daily many research is going on, synthesizing new drugs to overcome variety of infections. Daily we come across many bacteria is coming, many viruses coming to the world. There are many reasons for that. And coming to the shift basis. See why I'm showing what is molecular manipulation, what is infection, because I want to connect all these to the greener technique, how I have made it. So what is shift base? A shift base is an imine or azomethine which have a group C double bond N, and it is generally synthesized from amine. When combines with aldehyde or ketone, we get a shift base. So you can see there is a bond between C and N, that is C double bond N, which converts the amine and aldehyde or ketone to a shift base. Literature says that shift bases are versatile in nature. There is many literature which focus that shift bases are versatile in nature, and this made us to focus on shift bases. Shift base also gained the importance because of its variety of applications in pharmacological activities like antibacterial, antimicrobial, antiproliferative, anti-tumor, etc. So why don't we focus on the shift base? Already a lot of work is done on the shift base, but they have not focused on the greener technique. So if you go for greener technique, then it may be useful instead of going for a conventional technique which is creating a lot of pollution problems. Many literature is available. Coming to the green chemistry, Paul Anastas is a father of green chemistry, and green chemistry is about reducing the waste, reducing the materials, extra materials, reducing the hazards, reducing the risk, reducing energy, reducing the cost. So these are the main concepts or why we focus on the green chemistry. And green chemistry looks at the pollution prevention. The main intention is to prevent the pollution and also support the chemical process which are environmental friendly. Before starting my speech, I just want to show from where this green chemistry has taken its origin. The idea of green chemistry was initially developed as a response of Pollution Prevention Act in 1990, which declared that US national policy should eliminate pollution by improved design instead of treatment and disposal. So they started focusing on the design. Instead of creating the pollution, then focusing on how to prevent the pollution, we have to focus on the initial step. Why don't we design in such a way that it gives a very minimal pollution. In 1991, EPA, that is nothing but US Environmental Protection Agency, Office of Pollution Prevention and Toxics, has launched a research grant. So then they thought, so what way we can make the people or make the professors or scientists encouraged? So we have to give them some fund or some research grant so that they will focus on the green technique. So this is the fund first time they have released in 1991. EPA, in partnership with the US National Science Foundation, proceeded to fund basic research in green chemistry in early 1990s. And they have introduced a new award in 1996 that is nothing but Green Chemistry Challenge Award. So when this award started, then people started focusing. They have started giving a lot of funds, many presentations, many conferences, keep on increasing day by day. Even we can see today in omics groups, they have given a track for the green chemistry, separate track. Previously there was nothing, no one is focusing on that. But see, every conference they give a special attention for the green chemistry. So from this we can understand how much it is more important. So there are 12 principles of green chemistry. Wherever we go or wherever we listen the speech, they say there are 12 principles which we have to keep in mind before proceeding for experiment. So first principle is prevention, that is prevention of pollution. Second principle, atom economy. Use minimum number of atoms. Don't use so much of chemicals, so much of atom, bigger atoms, and just try to use a minimum atoms and try to create new molecules. Less hazardous chemical substances. Try to prefer the chemical substances which are less hazardous. Sometimes we should not think about commercial point of view. Sometimes you have to think about the environment point of view also. So if there are two chemicals, one is very reactive but it is very dangerous, very much pollution creating. The other one is maybe its reaction takes a little bit more time but it is very safe. Better go for the second one. This green chemistry principle says that prefer the ones which are environmental friendly. Design safer chemicals, safer solvents and auxiliaries, designing energy efficacy. Also they say they focus on the energy utilization. They say that we have to go for minimum energy utilization because the heat produced when a chemical reaction takes place is also reason for the pollution or environmental unsafe effect. Next, use of renewable feedstocks. Reduce the derivatives. Don't create large 32 derivatives, 40 derivatives which are of no use. Just think which derivative will be more effective. Try to synthesize 3 derivatives, 4 derivatives enough. No need to go for 30, 40 derivatives for any publications matters. Because I have seen that in many publications some of the reviewers write, you have synthesized only 4 derivatives. How can you find out? It depends on all the experience you know. Like according to my point of view, there is no use of synthesizing 30, 40 derivatives and check each and every activity and waste all the chemical. No. Before proceeding experiment, you just go have a thorough literature and try to select the derivatives which you feel like will be effective. So try to reduce the number of derivatives. Next, better use catalysts. So make the reaction a little bit more faster. So you have to focus, why don't we use a catalyst and make the reaction in 2 minutes instead of making a reaction for 2 hours, 3 hours extra. So we have to show our attention towards the catalysts. Next, design for degradation. Yeah, this is also very important. See, we know we synthesize many drugs and we leave it. As a scientist, we leave it. Nobody bothers how we degrade them, how we dismantle or whatever it is. If the drug gets expired, how to degrade it without causing any pollution to the environment. This is also a very important factor. You have to think from synthesis till degradation. How to synthesize and how to degrade if it is used it, or if it is unused, or it is waste. Next, real-time analysis for pollution prevention, inherently safer chemistry for accident prevention. So these are all the 12 important, very important principles of brain chemistry. Then how to achieve? Achieve through education. We have to educate our students from the UG level or basic level or the school level itself. We have to start training them the importance of green chemistry. There are many methods framing the experiments in the greener techniques. The same experiment you can follow using the greener solvents, using the catalysts, using a minimum quantity of reactants to get the products. So many techniques can be followed. There are many references for that which convert the traditional method of synthesis to the greener route. Okay. You can plan the projects, everything from the basic level or UG level or school level. If we start doing that, then this area will be focused more and we can be a part to reduce the pollution. Energy requirements should be recognized for their environmental impacts and they should be minimized always. And synthetic methods should be conducted at ambient temperature and pressure. So these are the points that you have to keep in mind before framing the experiment. How can we do that? There are many approaches. Just I have pointed few approaches. You can go for water or green solvents instead of many hazardous chemicals to synthesize new products. You can go for solvent-free synthesis, which is more focused nowadays, solvent-free. Without solvent, they are trying to synthesize new molecules. Next, microwave synthesis, ultrasonic reactions, photochemical synthesis, solid-supported synthesis, fluorous synthesis, and etc., etc., etc. There are many approaches. So now, what is the role of green solvent? It is very important, which is a minimum thing which we can frame the experiment. Just green solvent should have certain properties. If we check these properties, we can select the green solvent. It should be low toxicity, should have low solubility in water, easily biodegradable, should have higher boiling point and easily they can undergo recycling. So these points, if you keep in mind and select the solvents, these will lead the way to the greener techniques. Coming to the main part, which I have made a small experiment of synthesizing novel azomethines in a greener technique. All the solvents that I have used were from Sigma and Rich. Have found out the melting points, UV spectra, IR spectra, proton NMR, C13 NMR and mass spectra after synthesizing my compounds. So generally simple procedure what I followed is, have taken beta phenylacroline and combined with substituted amines. Both were taken in equimolar concentration. So now the solvent what I have used is ethanol, simple ethanol, which is not so much hazardous. So in that I have dissolved my sample and both the reactants, and then I have added catalyst, triethylamine. I have used a basic catalyst, triethylamine, went for mixing of these solutions about in a what is a magnetic mixer. I have not used for any reflexation or nothing, just stirring. Only stirring is my concept, where there is no heat production, there is no evaporation, nothing. So have gone for just a magnetic stirring. It has the product is formed. Temperature I maintain 60 to 70. It's not like room temperature, little bit higher temperature, ambient temperature like 60 to 70 degrees for 6 hours. I've made it stir for 6 hours. Maybe if I go for reflexation, it takes 3 to 4 hours, but lot of heat will be produced, but lot of vapors will be coming out. So maybe I wasted 2 hours, but I protected the environment. So this is one of the technique which we have synthesized azomethines SB1 to SB6. This is the scheme. Beta-phenylacroline with aromatic amines in the presence of ethanol, and triethyl amine is used as a catalyst at a temperature of 60 to 70 degrees centigrade. This is another simple technique. Same azomethines, I tried to synthesize in another green technique. These are all my own experiments. I was doing my own experiments in my lab. This what I have done, have taken same beta-phenylacroline and substituted amines in equimolar concentration. Just I have taken a mortar pestle. Everybody knows, I think, what is mortar pestle, because we start our study with the mortar pestle. When we go into the lab, we'll be very interested to mix with the mortar pestle. So I have taken the simple mortar pestle, triturated the two compounds, added the same catalyst, but trituration instead of refluxing and 60 to 70 degrees temperature and etc. etc. Even I want to avoid that also. I just want to go for physical exercise because it's a student level project I tried. So after triturating at room temperature for only 30 minutes, I got the product. And just same thing, I've tested the product which I have synthesized from the stirring and also synthesized from the trituration. So both the yield is almost same. Maybe little difference, it is a minor difference. So whichever route is, if you are physically, you don't want to work out, you can go for stirring method, and if you are very strong, you can go for the trituration method. This is a simple mechanism which is involved in my synthesis. This is amine. When I treat with a catalyst, the base will take the hydrogen from the amine. As the hydrogen is left, the nitrogen will be very reactive to occupy the place to react with the carbon. And the solvent takes an electron pair from C double bond O, and finally you get a intermediate with carbon substituted with OH. Now the base takes one more hydrogen from the nitrogen. Again, nitrogen becomes very unstable. To get it stabilized, it forms a double bond with carbon. So finally we get a shift base. This is the mechanism I thought it is involved in the formation of the shift base. So this is the physical data where I have compared the yield from first method to the second method. It's almost same. So I think any method can be followed. These are the IUPAC names given. I have given to my compounds. This is the data of UV visible spectra and IR spectra, data of proton NMR and C13 NMR spectra, data of mass spectra and elemental analysis. I have just shown one sample for how the mass spectra, the atom is fragmented, and how I confirm the weight of my sample. So I got a parent peak at 237 and base peak at 51, and different fragments I got at 160, 130, 107, 102, 77 and 53. This confirmed my molecule SB4 is as a shift base. So my synthesis part finish. Then I want to check at least what any compound should have minimum use, in what way it can be used. From the literature, as it is showing that it has antimicrobial properties, I want to check on bacteria. I have selected 4 bacteria. two bacteria from gram positive and two bacteria from gram negative. From gram positive, we selected Staphylococcus aureus, Bacillus subtilis, and gram negative, Pseudomonas aeruginosa and Klebsiella pneumoniae. Then I have gone for test tube dilution method and disk diffusion method. So made a stock solution of 2000 microgram per ml, diluted to 1500, 250 and 125. And I have added my bacterial suspension, incubated 37 degrees for 24 hours, and growth of the bacteria was checked. So then I have selected the minimum concentration and went for the disk diffusion method to find the zone of inhibition. And from that, I have found out that this is the data for MIC, minimum inhibitory concentration, and this is the data for the zone of inhibition. Out of my studies, I have found out that at a concentration of 250 microgram per ml, all the compounds from SB1 to SB6 have shown significant antibacterial activity. SB5 and SB6 were active against Staphylococcus aureus and Pseudomonas aeruginosa and also Klebsiella pneumoniae. SB3 is active against Bacillus subtilis and Staphylococcus aureus. SB3 active against Bacillus subtilis and Staphylococcus aureus. SB4 active against Pseudomonas aeruginosa and Staphylococcus aureus. SB1 and 2 are active against Staphylococcus aureus. So finally, I am happy to say I have now communicating with a good publication about this work. And I request, my personal request is, I want you all to try. You can go for your own method of synthesis. I don't want to disturb you. But if you can try in greener technique, it will be more useful for the environmental factors. Okay. So it's about time. I think time is also up. So I want to conclude this session. I want to conclude saying that green synthesis is a better way to synthesize beta-phenyl acrolein derivatives, and they also appear to be novel compounds and so also very active against many bacteria. And these are all the references. Thankful to the university which have given me the grant, and also I am thankful to the omics groups which has given me the platform to make a small coordination with all you people, all the professors. So my presentation is dedicated to the Schiff, Hugo Schiff. He has given me the molecule or mechanism, idea, whatever it is. I don't know where he is now. Okay, thank you so much, Mr. Schiff, Dr. Schiff. And this is my small team, which is in the graduate level. I am training them to go for the green technique. Thank you. Thank you so much.